Welcome to this explainer. Today, we're embarking on a pretty monumental journey into the very heart of matter itself. We're going to trace the fascinating steps of humanity's quest to figure out the physical world. We're literally moving from ancient, smoky mysteries all the way to the rigorous scientific rules that shape our modern universe. Which brings us to a really profound mystery. Where exactly does the magic of alchemy end and the actual science of chemistry begin? It's this incredible historical puzzle. We're looking at the literal birth of modern science, rising straight out of the ashes of mysticism, endless trial and error, and just a relentless human curiosity about what makes up the world around us. So here is a quick roadmap for our journey today. 1. From alchemy to chemistry. 2. The birth of modern science. 3. Atoms and molecules. 4. The language of chemistry. And finally, 5. The central science. Section 1. From alchemy to chemistry. Let's dig right into the ancient, kind of mystical roots of all this chemical curiosity. Okay, let's start with the etymology, because the history packed into this single word is just staggering. The word chemistry is a direct descendant of alchemy, and the origins of alchemy itself, beautifully diverse. We have the Arabic alchemia, where al simply means the, but if you dig a bit deeper, you find the ancient Greek word hemia, which was all about the art of alloying metals, casting them together into something brand new. Or actually, it might trace all the way back to the ancient Egyptian word chem, meaning blackness or black earth, which was a total nod to the rich, dark, fertile soils of the Nile River Valley. So right from day one, this practice was deeply rooted in the earth and the transformation of materials. Now, early alchemy was a heavily visual and highly mystical pursuit. Practitioners were absolutely obsessed with this idea of chrysopoeia, the transmutation of base metals into gold or silver. The goal was to create these brilliant, shining metallic surfaces and perfectly reflective gemstones. Honestly, back then, it was just as much an art form and a philosophical journey as it was a physical one. But behind closed doors, the reality of those early laboratories was, well, a bit less glamorous. It was totally chaotic. Early experiments relied almost entirely on brute force trial and error. You'd basically just heat something up, toss in another liquid, and cross your fingers. Often, this highly experimental approach ended in strange foams, terrible smells, and literal explosions. Honestly, it was an ancient OSHA violation just waiting to happen. There was zero standardization, just isolated practitioners trying to unlock the secrets of matter through sheer persistence. Section 2. The birth of modern science. This is where things really take a turn. In the 18th century, a pivotal era when magic finally started transforming into a strict mathematical science. It's wild to think about how people used to understand the world compared to now. Take the old phlogiston theory, for example. People actually believed that burning a metal released this invisible, mysterious substance called phlogiston, leaving behind a flaky residue called a calx. Actually, scratch that. It wasn't just mysterious, it was completely backwards. Compare that flawed logic to the revolutionary precise chemical equations we rely on today. Solid lithium reacting with oxygen gas to form solid lithium oxide. Boom. No magical invisible substances, just exact, measurable, totally predictable elements rearranging themselves. And the undisputed hero of this transition was Antoine Lavoisier. In 1787, Lavoisier, working with a few other brilliant minds, completely reformed the field. He realized that to break free from the mystical symbols and secret codes of alchemy, science desperately needed a new, standardized language. He essentially set out to make a chemistry logo, a universal brand identity where every single compound had one specific, unambiguous name based on its exact components. This was a massive, game-changing paradigm shift that officially ripped chemistry away from alchemy. Section 3. Atoms and molecules. So what exactly are the building blocks that Lavoisier's brand new scientific language was designed to describe? Well, the absolute fundamental piece of all matter is the atom. It's the basic unit of a chemical element. And even though those early chemists couldn't physically see them, we now know that atoms themselves are built out of even smaller subatomic particles, positively charged protons, neutral neutrons, and negatively charged electrons. Everything around you right now, the screen you're looking at, the air you're breathing, is made up of these incredibly tiny, indivisible building blocks. I really love the language metaphor we can use here. Think of individual atoms like the letters of an alphabet. A single atom, with its nucleus and orbiting electrons, is just one letter. But when you start connecting those atoms together using chemical bonds, they form molecules, multi-atom combinations that start behaving as a single particle.
Just like letters combine to form molecular words, the entire incredible diversity of our universe is literally just different combinations of these atomic letters.
But you might be wondering, why do they combine? Why do two compounds react in the first place? It really boils down to one key concept: favorable thermodynamics. In very simple terms, atoms rearrange themselves, breaking old bonds and forming new ones because the energy holding the new bonds together is more stable than the initial bonds. Nature just loves stability. That thermodynamic drive is the engine behind absolutely every chemical reaction. Section 4, the language of chemistry. Now let's explore exactly how chemists actually write out the sentences of this science using specific nomenclature and equations. Building on Lavoisier's legacy, chemistry developed these foolproof rules for chemical nomenclature. It's a beautifully logical system where every single compound gets its own unique name and formula. The steps are so straightforward. First, you identify the elements in the molecule. Second, you write down their specific symbols from the periodic table. And third, you just add numerical subscripts to show exactly how many atoms of each element are in there. It's totally unambiguous. Dinitrogen pentoxide will always, everywhere, mean N2O5. So let's see how these molecular words form actual sentences, what we call chemical equations. Say we have hydrogen gas, H2, plus oxygen gas, O2, forming water, H2O. The reactants are on the left, the product is on the right. Makes sense, right? But wait, we have a glaring problem here. If you think about it, we start with 2 oxygen atoms on the left side, but end up with only 1 oxygen atom in the water molecule on the right. We literally lost an atom. And that's a huge issue because it completely violates the law of conservation of matter, which states that matter cannot be created or destroyed. To fix this, we have to balance the equation. We simply count the atoms on each side, adjust the big coefficients in front of the molecules, and then verify that the elements are perfectly equal. Remember, we can't change the underlying formula, but we can change the amounts we're reacting. And here is the triumphant result. By putting a 2 in front of the hydrogen and a 2 in front of the water, the whole thing balances perfectly. 4 hydrogens on the left, 4 on the right. 2 oxygens on the left, 2 on the right. We even toss in some phase labels, like the little G for gas and L for liquid, just to be totally precise. This perfectly balanced equation beautifully captures the sheer elegance of modern chemical language. Section 5, the central science. Finally, let's zoom way out to show how all these microscopic rules apply to the macroscopic world around us. Because this universal language of atoms and bonds applies to literally everything in existence, chemistry naturally splits into distinct branches to tackle the vastness of matter. You've got organic chemistry, which focuses on carbon-based compounds. So that's the chemistry of life, living organisms, and pharmaceuticals. And then you have inorganic chemistry, which studies basically everything else: metals, minerals, crystals, solid-state materials, ceramics. Literally every physical object you interact with falls under one of these massive umbrellas. Which leads perfectly to this really powerful statement. Chemistry, the central science, holds interdisciplinary technologic advances together. And listen, this isn't just chemists bragging. Because chemistry studies the very matter that constructs the universe, it acts as the ultimate vital glue. It connects the hard, fundamental laws of physics with the incredibly complex biological systems of life. You simply cannot have advancements in medical tech, environmental science, or space exploration without a really deep understanding of chemistry. Which leaves us with this final, thrilling thought to ponder. From the magical, smoky cauldrons of early alchemists to the perfectly balanced, elegant equations of modern science, humanity has learned to read and write the alphabet of the universe. So, if chemistry truly is the language of matter, what unwritten chapters of technology are we going to translate next? Thank you so much for joining me for this explainer. Keep that curiosity burning, and I'll catch you next time.